You hear our introduction to limits in the textbook with the properties of limits and direct substitution. So last week what we focused on was we focused on a numerical approach and we focused on a graphical approach. All right, so again, earlier in the year I said that everything we do, we want to master it in terms of the three facets. So we want to do numerical, graphically, and algebraically. So what we're going to do now is we're going to work on this stuff a little bit more algebraically. So one of the things I think that a lot of you kind of noticed, especially from last week, is that oftentimes the limit of a function is pretty much the value of the function at the x location. Okay, so what I mean by that is most of the times we're going to have a limit as x approaches some number. We're going to call that the constant. In most cases, it's just going to be f of c. So in most cases, it's just going to be you plug in the value of c into the function and you would get your value out, right? We did that numerically a bunch of times. We also looked at that in the graphical sets last week. All right, so this is a kind of common occurring theme, but it does not always work, right? Especially for cases that we see where you have an undefined location or you have a hole in a specific location. So it's not always going to work, but this is the very basic algebraic form where all you have is kind of substitute the value of c. Now this works very well with what we call the well-behaved functions. All right, so well-behaved functions are usually functions that exist throughout the entire real number system. So for example, polynomials are well behaved because their domain is all real numbers. A typical sine function is well behaved. A typical cosine function is well behaved because they have no holes, there are no asymptotes. They kind of all, work nicely together. Where it gets more complicated is once you start to combine some of these functions. For example, if you took a rational function, which is a combination of a polynomial divided by a polynomial, you can run into some issues in certain locations for the x values, especially when you're to get an undefined location. So again, it all depends on the function. So what we're going to do is we're going to be working with a lot of well-behaved ones. So this section isn't going to feel too difficult, but it is important to understand the properties of limits and direct substitution, how that applies, because you're going to see that more often later on, where we have some little tricks of the trade to kind of find our limit. All right, so some basic limits. So these are some very, simple cases. So again, this is something for your notebook. Just pay attention to what the function we're working with here. All right, so it's the limit of b as x approaches c is equal to b. Now b is going to be a real number because it's stated up here. So in a sense, you're just finding the limit of a constant. So for example, if we had the limit as x approaches 1 of 6, well, 6 is a horizontal line. It's constant, so it's never going to change. So the value of y is always going to be 6. So as x approaches 1, it's going to be equal to 6. So that's pretty much the first one, right? Not too crazy on that one. The second one, okay, works with the
7:30 a.m.
The next one works with the limit as x approaches a constant of the function x. Right, so we know that the function x is just the y equals x line, which goes to the origin. And what we know based on the y equals x line is all the points on this specific line. If x is the coordinate, y is also the coordinate. All right, so we know that 2, 2 is a coordinate, 3, 3 is a coordinate, -1, -1 is a coordinate. So this value here is just going to be 2. All right, so that's just, again, another basic concept. All right, the limit as x approaches, let's say, -1 of x to the, let's say, third power. All right, well, again, that's just a substitution, so it's just going to be a -1 to the third based on the basic limit above. Whatever we're approaching gets raised to the third power, so again, that's just going to be equal to -1. Okay, the same thing with the last one is what is the limit as x approaches 16 of, let's say, the square root of, or let's do the fourth root, make it more complex, of x. So again, you're just going to be taking the fourth root of the value you're approaching, and then that's going to be equal to plus or minus 2. And we're going to go with the positive form of the radical, so 2. All right, so again, not too bad. It's just, as you can see, just mostly substitution here. So let's go on to the properties of limits. All right, so now these are properties of limits. So the idea, they all help us out later on. So what you want to understand is, like, if the first one is you're taking the limit of a function times a coefficient. So like, for example, if we had, let's say, 2x squared minus 4x, right? Technically, you can factor that out into 2 times x squared minus 2x. So the limit is just going to be 2 times the limit of this function. Okay, so whatever the limit gives you of the factor, then you're going to multiply that by 2, and that's going to give you the limit. You could have just done that easily without having a factor, but there's some cases where they're going to have a number multiplied by a function. So just find the limit of the function in parentheses here, and then multiply by 2, and you'll still get the same answer. Okay, that's the beautiful thing about working with the constant, is that you don't really need to factor it out, but if it is there, it just makes your life a little bit easier. All right, the second one here is the limit of functions that are combined. Okay, so certain times polynomials can feel that way, but you can have a sum of 2 different functions. So if you have a sum or a difference of 2 different functions, then just find the limit of the first one and then add it or subtract it to the limit of the second one. Okay, k here represents the other limit of g. Okay, so that's what you're doing. Find the limit of the first piece, find the limit of the second piece, add those 2 values together, and you get the limit of the entire sum or difference. Same thing with the product, right? If you're multiplying f times g, find the limit of f, which is L, find the limit of g, which is k, and then you do the operation and you multiply them. Okay, same thing here with the quotient. Find the limit of f, which is L, find the limit of g, which is k, divide. Now here is very important because the limit cannot equal 0 in the denominator, because we know that that's going to be an undefined value. Okay, and then the last one is kind of like a composition. It's kind of like one of those functions where you have, like, let's say x squared plus 1, but then raised to the 7th power or something like that. So all you have to do is find the limit inside here. Once you find the limit on the inside, then you're just going to raise that limit to the 7th power at the end. All right, so you're going to just work on it just basically the same way you would in a specific composition. All right, so all these properties are kind of just similar. They feel natural because you've been doing these properties for so often. So the same thing applies to limits. So we can kind of work with that accordingly. All right, so let's actually get into it. Let's find some limits here. All right, so let's look at A. We're looking at the limit as x approaches 4 of x squared. Okay, so as x approaches 4 of again, that's a polynomial. It's very well behaved. It's a parabola. So all we have to do here is we're going to substitute 4 into the function, and that's going to give me positive 16. So the limit is going to be equal to positive 16. Again, we can confirm all this graphically and numerically. All right. Again, this is just the algebraic approach, a very simple algebraic approach. Right, so the limit of the function 5x as x approaches 4, well, that's just going to be 5 times 4, and you're going to get 20 as your limit. All right, third one, here's a trigonometric one. Again, understanding trigonometric values is very important for when we do limits. Okay, so it's a rational one, so you're going to do the limit of the top and then the limit of the bottom. So as x approaches pi in the top, so that's going to be equal to 0 in the numerator, tangent of... Well, let's write it out so you guys can see. Let's do tangent. We're going to substitute pi over x. I wrote pi earlier. So this is over x. So we're going to substitute the pi. So tangent of pi is 0 divided by pi. 0 divided by pi is 0. So the limit as x approaches pi of tangent x over x is going to be equal to 0. Again, all of these were just substitution. Direct substitution is the method we're going to be learning this week. All right, so again, not too bad because we are pretty proficient at our algebraic skills. right, so D, we have the limit as x approaches 9 of the square root of x. So we're going to do the square root of 9 because that's the value we're approaching, and the square root of 9 is equal to 3. So there you go. Again, they only gave us the positive value, so we're going to stick with the positive value, right? If they put a plus or minus here, then we would include both values, but they did not, okay? All right, so here, let's do the limit as x approaches pi of x cosine x. Okay, so here's one that you kind of want to use the property for. Again, since it's a product, we can write this as the limit of the first part of the product, which is x, times the limit of the second part of the product, which is cosine x. All right, so we can split that up so we can use the property. All right, so what's the limit of x as x approaches pi? Well, that's just a substitution. You're going to get pi times, right? What is the limit as cosine of x approaches pi? So at cosine, the cosine function as x approaches pi is going to be equal to -1. So x times -1, and you're going to get negative pi as your limit. All right, so that's going to be the value of the value of y that you're going to approach as x approaches pi. Okay, all right. The next one is the limit as x approaches 3 of x plus 4 to the second power. All right, so again, what you can do is you could just find the limit on the inside and then raise it to the power. But again, using just direct substitution means that's pretty much what we're doing anyways, using the order of operations. So we're going to get x is now 3 plus 4 to the second power. That's going to give me 7 to the second power. 7 to the second power is 49. Okay, so the limit as this function approaches 3 is going to be equal to 49. Okay, limits of polynomial rational functions. All right, so here, if p is a polynomial function and c is a real number, then the limit of the polynomial as x approaches a value is going to be p of c. Like I said before, since polynomial functions are very, very well behaved and they exist everywhere, it's just going to be a matter of direct substitution. So that's basically what they're telling you. So just to find the limit of any polynomial function, just take the direct substitution. It's a quick and easy method. All right. Now, it says if r is a rational function, where the rational function is the quotient of two polynomials, and c is a real number such that the denominator, when you plug in that value, does not equal 0, then you have a limit. Right, so now again, we are kind of only focusing on values of c that are not going to make my denominator equal to 0. We know that there's many, many cases that's going to give us denominators of 0, but they're specifically telling us here, all right, that the ones we're going to be substituting are not going to be making our denominator equal to 0. So again, just direct substitution is going to work. Substitute into the polynomial in the numerator, substitute the polynomial in the denominator. We're perfectly fine, and all the ones already working in this section. It's in the next section where we actually start to get into issues where we have zeros in our denominator. Okay, so let's find these two limits, and then we're done. All right, so here we go. The first one, we are going to find the limit as x approaches -1 of x squared plus x minus 6. Now, it's a polynomial. We know polynomials are very well behaved, so all we are going to do is we're just going to substitute, okay? So we get -1 squared plus -1 minus 6. We're going to get 1 minus 1 minus 6. So the limit as x approaches -1 is going to be -6. Now I do want to show you how the property of the sum and difference will also work here, because technically we're adding and subtracting these three terms. So it's the same thing as if I said, okay, what's the limit of -1 of x squared plus the limit as x approaches -1 of x minus the limit as x approaches -1 of 6. And you're going to see that you're going to get the same result either way. So this is just going to be -1 squared. This is going to be -1. And we know that this is going to be -6. We know that's the same sum. So we get negative 6. Right, so that's how we know that polynomials work very well, is because these basic definitions of the limit, so this one, and this one, okay, all these three basic definitions are ones we learned. The limit of a constant, the limit of the nice x function, and then the limit of a function raised to a power. Those three combined make a polynomial. Very simple, okay? All right, let's look at the second case here. So let's get rid of this. Again, pause the video if you need to see the work for the previous one. All right, so let's work on B. All right, so I'm just going to do this using direct substitution. So we're going to look at the limit as x approaches -1 of the rational function x plus 3. All right, so now really quickly, just so you know, right, we just have to avoid that the denominator is not going to be equal to 0. And as we can see, the -1 is not going to do that for us. So we are okay to just use direct substitution. Because again, a rational function, most of the time, it's just going to be a polynomial divided by a polynomial. And we know with polynomials, direct substitution works wonders, right? So here, in the numerator, it's going to work. In the denominator, it's going to work because it's not giving us 0. If you give us 0, that's a different story. All right, so now we have -1 squared plus -1 minus 6. All right, and in our denominator, we're going to get -1 plus 3. So in my numerator, I get +1 minus 1 minus 6. In my denominator, I get -1 plus 3. So that's going to give me -6 over 2. So the limit is going to be equal to -3. Okay, so -3 is the limit that the function is approaching as x approaches -1. All right. Okay, so again, this ends up, our first section in our calculus topics, which is Introduction to Limits. Very easy idea right now. We will get into some more complex stuff as we move on a little bit. But again, we kind of evaluated limits in 3 ways, and that's very important. Okay, we did it numerically using tables. We did it graphically. And we did it algebraically. Now, moving forward, it's going to be important for us to be proficient at all 3 methods, because sometimes it's very difficult to do one algebraically, so understanding how to do it graphically will help you. Sometimes numerically makes things a little bit easier, so again, numerically will be the approach we take. All right, so knowing all 3 will be very, very beneficial, especially once you start getting to some higher level topics of calculus. All right, so thanks for watching. Hopefully this video was very informative.